Hello friends, today we are going to read the chapter of inorganic chemistry that is known aqueous solvents. So let's start. Most of the chemical reactions are carried out in solutions and the behavior of substance also depends upon the nature of solvent. In the earlier days of the development of chemistry, the reactions have been carried out only in one solvent, namely water. It has been facilitated by its ready availability, ease of purification, together with its favorable physical and chemical properties such as long liquid range 0 to 100 degrees Celsius, high dielectric constant, specific heat, heat of volatilization, type of movement, etc. Water is neutral, odorless, non-toxic, and non-poisonous also. It can therefore be handled safely. The properties of water make it an excellent and useful solvent for a large variety of substances. In fact, the excellent properties of water have hindered the development of non-aqueous solvents. The solvents other than water, which are used for carrying out chemical reactions, are called non-aqueous solvents. Attempts have been made to find some other substances which could behave as a good solvent like water. The organic chemists have been using many solvents such as benzene, carbon tetrachloride, acetone, ether for dissolving organic compounds which are insoluble in water. Now are many other soluble so there are many other solvents available, for example liquid ammonia, H2SO4, liquid HF, liquid sulfur dioxide, etc., which have been frequently used. In the present unit, we shall discuss briefly the important feature of non-aqueous solvent such as ammonia and SO2. Physical properties of solvents and their role in chemical reaction. The usefulness of a solvent is determined from its some specific properties that may help to carry out the chemical reaction and separate the products more conveniently. Some of the important physical properties of solvent are discussed below. Melting point and boiling point, liquid range. The melting and boiling point of a solvent determine the temperature range within which the solvent can exist in the liquid state under atmospheric pressure. Since most of the reaction in the solvent system are carried out in liquid phase, the melting point and boiling point give the temperature range within which solvent is useful. The melting and boiling points for some common solvents are given in the table. Some, for example, for water, melting point is 0 degrees Celsius and boiling point is 100 degrees Celsius. For ammonia, the melting point is minus 77.7 degrees Celsius and boiling point is minus 33.4 degree Celsius. It is clear from the above table that water has an excellent liquid range 0 to 100 degrees Celsius at ordinary temperature and pressure. Acetic acid can also act as a solvent at ordinary temperature, while ammonia and SO2 can also act as a solvent at low temperatures. Heat of fusion and heat of vaporization. The value of heat of fusion and heat of vaporization help to know the nature and strength of forces which hold the molecule of the solvent together in a solid or the liquid state. As we know, the amount of heat absorbed by 1 mole of a substance to change from solid to liquid state is called molar heat of fusion. Similarly, the heat absorbed by 1 mole of the substance to change from liquid to vapor state is called molar heat of vaporization. The large value of heat of fusion or the heat of vaporization, the stronger the intermolecular binding forces in the solid or the liquid respectively. Therefore, the magnitudes of molar heats of fusion and molar heat of vaporization give us some insight into nature and strength of intermolecular forces, and these also determine the solvent properties. A better idea for intermolecular forces in a solvent is obtained by the ratio of molar heat vaporization to the boiling point. This ratio is called Thornton constant. Constant can be found out by dividing the enthalpy of evaporation to the boiling point. It can be denoted del H evaporation upon TB. For normal liquids, If molar heat of vaporization are expressed in calorie and boiling point in absolute scale 0 degree Kelvin, then the total constant has the value of 21.5. Such liquids exist as an independent molecule without any bond between them. A higher value of proton constant indicate associated molecules. For example, common solvents like water, ammonia, hydrogen fluoride have a total constant value greater than 21.5 and are therefore associated liquids. The molecules of these liquids are polar. The association of polar molecules is due to their tendency to orient themselves so that the oppositely charged end of molecule come near to each other. Molar heat of fusion and vaporization of some solvents. Water molar heat of fusion is 6 and molar heat of vaporization in kilojoule per mole is 40.65. For ammonia, they are 5.65 and 23.56 respectively. For SO2, they are 7.40 and 24.94 respectively. The inspection of table 2 show that the value of molar heat of fusion of water and ammonia are almost same. This means that forces which hold molecule together in water and ammonia are of same magnitude. Dielectric constant. This property is a measure of polar nature of solvent and help to estimate the solubility of polar and non-polar substances in the solvent. According to the Coulombic law, the forces of attraction between two charged ions are given by F Q positive Q negative upon E R square, where Q positive and Q negative are charges of the cation and anion respectively. R is the distance between them and E is the constant called dielectric constant of solvent. If E is larger, the force F will be smaller. As the result, only a small amount of energy will be required to separate the ions and hence will be easy to dissolve an ionic substance. Thus, in solvent of high dielectric constant, the ionic substances will dissolve readily. With the decrease in dielectric constant, the solubility of ionic compound will decrease and the dielectric constant of some common solvents are given in the table. For water, 81.7 at 18 degrees Celsius. For ammonia, 22 at minus 33.5 degrees Celsius. For SO3, 17.3 at minus 16 degrees Celsius. For acetic acid, it is 9.7 at 18 degrees Celsius. It is clear that above solvents like HF, H2O are good solvents for ionic and polar compounds because of their high dielectric constant values. On the other hand, solvents like ammonia, SO2 with small value of dielectric constant show decreased tendency to dissolve ionic compounds and especially those containing multi-charged ions, for example carbonate, sulfate, phosphate, and practically insoluble in liquid ammonia or liquid sulfur dioxide. Dipole moment is related to dielectric constant of the solvent. An ionizing solvent has a large dipole moment and also has a large dielectric constant. It is related to the polarity of the bond in the molecule. Greater the polarity of the bond in the molecule, larger is the dipole moment. Solvent having high dipole moments have greater tendency to dissolve the polar and ionic substances. This is because of the fact that greater the polarity results in strong bond between the solvent and the solute molecules and larger solvation energy is released. This large solvation energy is sufficient to overcome the lattice energy in the solute molecules and help in dissolving the solute. Viscosity. It is the measure of fluidity of a solvent. Solvents like water, ethyl alcohol, carbon tetrachloride having low viscosities and high fluid are highly fluid and flow rapidly under ordinary temperature. On the other hand, anhydrous sulfuric acid and high molecular weight hydrocarbons have high viscosities and flow at much lower rate at ordinary condition. In solvents of low viscosity, the operations such as precipitation, crystallization, filtration, etc. can be carried out without any difficulty. With increasing the viscosity of a liquid, increase the difficulty of such operation. Types of solvent. Non-aqueous solvents have been classified in many ways. The following are the important classification based upon the chemical properties of the solvents: protonic and non-protonic solvents, acidic or basic or amphiprotic solvents, ionizing and non-ionizing solvents, coordinating and non-coordinating solvents. Protonic and non-protonic solvents. The solvents from which proton can be derived are called protonic or protic solvent. Therefore, protonic solvent contain ionizable hydrogen. Common examples are H2O, HF, H2SO4, HCN. The solvents from which protons cannot be ordinarily derived are called non-protonic solvents. They are called aprotic solvent. In other words, the solvent do not contain ionizable hydrogen atom. For example, liquid SO2 and 2O4, C6H6, CHCl3, CCl4. Amphimorphic or acidic basic solvents. This classification is based upon the acidic or basic behavior of solvents. The solvents which have a strong tendency to donate proton are called acidic in nature and are called acidic solvents or protogenic solvents. For example, H2SO4, liquid hydrogen fluoride, acetic acid. Solvents which have strong tendency to accept proton are called basic in nature and basic or protophilic solvents. Example, ammonia, pyridine, hydrogen, ethylene diamine. The solvent which neither have strong tendency to gain or nor the strong tendency to lose protons are called amphiprotic or amphoteric solvents. In other words, they neither behave as a strong acid nor basic, but can behave as acidic as well as basic depending upon the nature of reacting species. For example, water, ethyl alcohol, methyl alcohol, ionizing and non-ionizing solvents. The solvents which are capable of undergoing self-ionization or auto-ionization are called ionizing solvents. For example, H2O, NH3, HF, SO2, N2O4, SClF3, BRF3, POCl3. These solvents are generally polar or ionic in nature. And on the other hand, the solvents which do not ionize at all are non-ionizing solvents. For example, benzene, carbon tetrachloride, hydrocarbons, etc. These are non-polar or non-ionic in nature. Coordinating or non-coordinating solvents. The solvents which are capable of coordinating with metal ions or anions of the solutes are called coordinating solvent. For example, NH3SO2 dimethyl sulfur dioxide DMSO, acetonitrile CH3CN, dimethyl formide DMF, nitromethane CS3NO2, for example, etc. On the other hand, the solvents which are not capable of coordinating with metal ions or anions of the solute are called non-coordinating solvents. For example, CCl4, saturated hydrocarbons. These are not of much interest to organic chemists. Type of reaction in non-aqueous solvents. Hmm. The following type of reaction commonly occur in non-aqueous solvents: metathetical or precipitation reaction. The reaction in which precipitation occurs on mixing two solutions are called metathetical or precipitation reaction. For example, AgNO3 plus BaCl2 gives 2AgCl in the form of PPT and BaNO3 twice. On the other hand, in liquid ammonia, a precipitate of silver chloride combined with barium nitrate to give precipitate of barium chloride, leaving silver nitrate in solution. Therefore, the reversal of a chemical reaction takes place on changing the solvent. Similarly, sodium hydroxide is highly soluble in water, but it can be precipitated in liquid ammonia. Water soluble copper sulfate may be precipitated in anhydrous acetic acid. Salt formation. The reaction between appropriate acidic and basic substances to form salts are called salt formation reaction. In such cases, the solvent used must be one in which the appropriate acid and base can exist. For example, sodium urate cannot be prepared by reaction of urea and sodium hydroxide in water. It is because the strong base available in water will not take the proton from urea molecule. In other words, the sodium salt of urea is unstable in water and ureate ion will take a proton from water to form hydroxide ion. However, this salt can easily be formed in liquid ammonia solution by reaction of urea with strong base soda amide. Acid-base reaction. The acid-base reaction in non-aqueous solvent can be explained on the basis of solvent system concept. As already learned, according to solvent system concept, an acid is a substance that by direct dissociation or reaction with solvent give the cation characteristic of solvent. Similarly, a base is a substance that give anion character of the solvent. Acid-base behavior of substance depend upon the acid Base nature of solvent, the character of solute, and the solute-solvent interactions. In case of protonic solvents, cation is the solvated proton and Bronsted protonic concept is same as the solvent system concept. For example, in liquid ammonia solvent, NH3 positive, NH4 positive ions act as acid and NH2 negative ion act as base. The neutralization reaction is carried out and it forms salt and solvent. In non-protonic solvents such as benzene, CCl4, Lewis base, acid-base type of reactions can occur because of the non-ionization of solvent. The acid-base behavior of a solute in a solvent depend upon the acidity or basicity of the solvent. For example, acetic acid behaves as a strong acid in ammonia, weak acid in water, but base in sulfuric acid. Solvolytic reaction or solvolysis. The reaction in which the solvent molecule react with solute in such a way that the solvent molecules split up into two parts, one or both of which get attached to solute molecule or ion, are called solvolytic reaction. Since these reactions occur through self-ionization of solvent, the concentration of either the cation or the anion is changed. For example, solvolytic reaction in water, ammonia, and ethanol are given. Solvation. The reaction in which the molecules of a solvent can get attached to solute species are called solvation reaction. The species formed is called solvate, and the solvation reaction in water, ammonia, alcohol, etc. are called hydration, ammoniation, alcoholation, etc. And the resulting solvates are called hydrate, ammoniate, alcoholates. Solvation of a cation occurs through ion dipole interaction between the positive cation and the negative end of dipole through coordinate bond in which the solvent molecule donates a pair of electrons to cation. On the other hand, solvation of an anion occurs through ion dipole interaction between the negative ion and positive end of a solvent dipole or through hydrogen bonding in case of solvents such as water, ammonia, and hydrogen fluoride. It may be noted that in certain cases it is difficult to distinguish between solvation and solvolysis because in many solvolytic reactions the first step consists of solvation reaction. However, the term solvation is used for those reactions in which the solvent molecule remain in the as the resulting product. Liquid ammonia. Liquid ammonia is also one of the most extensively used known aqueous solvent. It is now used as a highly useful solvent and the reaction medium for many types of organic and inorganic synthesis. Its most of the physical properties resemble those of the water. The comparison of properties of liquid ammonia and water. Liquid range. The melting and boiling point of liquid ammonia are lower than that of water. Liquid ammonia, the liquid range is in form of -77 to 33 degrees Celsius and therefore it presents some handling problem. Therefore, some precautions have to be taken while using liquid ammonia as solvent. It generally handled in cold vessels, and nowadays wide range of techniques have been advanced for handling it. Hydrogen bonding. Like water, liquid ammonia is an associated solvent through hydrogen bonding because it contains a strongly electronegative element nitrogen. However, ammonia molecule are less strongly associated because nitrogen is less electronegative than oxygen and therefore NH bond is weaker than OH bond. As the result, the freezing point and the boiling point of ammonia are less. Since ammonia is less associated than water, it is better solvent for organic compounds. Dielectric constant. The dielectric constant of ammonia is lower as compared to water, suggesting its lesser tendency to dissociate ionic compound. Liquid ammonia is therefore a poor solvent for ionic substances. Soluble salts include most ammonium salts, nitrates, thiocyanates, and iodides. Fluorides and many oxysalts are generally insoluble. However, ammonia has low viscosity than water, and this might be expected to promote greater ionic mobilities and thereby compensate to some extent of effect of dielectric constant. Self-ionization. Both ammonia and water show comparable self-ionization as represented. However, the extent of auto-ionization of liquid ammonia is less than that of water. This is clear from this have specific conductance and lower ionic product. For ammonia, it is 1.9 into 10 raised to power minus 23 at minus 50 degrees Celsius, and for water, it is 1 into 10 raised to power minus 14 at 25 degrees Celsius. Therefore, ammonia can conduct electricity to a feeble extent. Ammonia is a better solvent than water. Liquid ammonia is very poor conductor of electricity. The specific age of ammonia is more than that of water. Liquid ammonia is less viscous than water. Most salts, when dissolved in liquid ammonia, conduct electric current better than in water. This is not due to ionization power of ammonia, but due to low viscosity, which generally greatly increase the mobility of ions. Liquid ammonia has a high critical temperature and pressure. It is less associated than water, and therefore it is better solvent than for organic compounds. Liquid ammonia forms strong reducing metal ammonia solution with alkali metals, therefore it is an excellent solvent for many reduction reactions. The reactions in liquid ammonia. Acid-base reaction. The acid-base reaction in liquid ammonia can be easily understood by comparing the reaction in water. According to the solvent system concept of acid base, the substance producing H3O positive ion in water act as an acid, while those producing OH negative ion act as a base. Liquid ammonia ionizes as NH4 positive and NH2 negative. Therefore, the substances producing ammonium ions NH4 positive in liquid ammonia behave as an acid, while producing amide ion NH42 negative as behave as bases. For example, ammonium salts such as ammonium halide, thiocyanate, nitrate, soluble in liquid ammonia behave as acid. Similarly, amide and nitrites behave as bases in liquid ammonia. The commonest base in liquid ammonia is potassium amide KNH2, which ionize as K positive NH2 negative. Lithium amide, sodium amide, alkaline earth metal amide have low solubility, and therefore KNH2 is the commonest base in liquid ammonia. Proteolysis. Certain compounds like urea, acetamide, sulfamide, etc., which are incapable of donating protons to water, can readily donate protons to ammonia in liquid, proton to NH3 in liquid ammonia. These reactions are called proteolysis reactions, hence these compounds act as acids in liquid ammonia. Sulfamic acid behave as a diabasic acid in liquid ammonia. However, it behaves as a monobasic in aqueous solution because NH2 group cannot donate a proton to water. Sulfamic acid behaves as a monobasic in aqueous solution. Acid-base neutralization. In aqueous solution, the process of neutralization of strong acid and strong base involve the combination of H3O positive from acid and OH negative from base to form practically unionized water. For example, the neutralization of HCl and sodium hydroxide may be represented as HCl plus NaOH gives NaCl plus H2O. H3O positive plus OH negative gives 2H2O. In similar way, the neutralization of an acid and a base in liquid ammonia involves the combination of NH4 positive ion and NH2 negative ion. There are many examples of amphoteric behavior in liquid ammonia. The compounds that dissolve both acid and base are called amphoteric substances. For example, in liquid ammonia, zinc amide show amphoteric behavior analogous to that of zinc hydroxide in aqueous solution. Reaction of amino acids. Amino acids is a substance that furnish NH4 positive ion in liquid ammonia. Ammonium halides, nitrates, or thiocyanate are very soluble in liquid ammonia, giving NH4 positive ion, and their concentrated solution act as amino acids. We know that the acids give hydrogen with metal in aqueous solution. In similar way, the amino acids react with alkali and other metals to give hydrogen. A saturated solution of ammonium nitrate in ammonia also dissolve many metal oxides similar to their behavior in aqueous acids. Solution of ammonium halides in liquid ammonia may be used as acid in preparation of saline and arsine. Reaction of ammonobases. Ammonobases is a substance which in liquid ammonia solution given as 2 negative ion. The commonest base is potassium amide, which is much more soluble than lithium and sodium amides. Metal salts reacts with ammonobases to give amides or nitrites, which get precipitated in liquid ammonia. Precipitation reactions. Precipitation reaction involves double decomposition because of the difference in solubility of various substances and water in liquid ammonia. A large number of precipitation reactions which are not normally possible in water have been reported to occur in liquid ammonia. Silver chloride is precipitated in aqueous solution. Similarly, a white precipitate of barium chloride is produced when solution of silver chloride and barium nitrate in liquid ammonia are brought together. Lithium chloride may be precipitated by the reaction of ammonium chloride and lithium nitrate in liquid ammonia. Iodides and bromoiodides get precipitated when solution of various nitrate and ammonium halides in liquid ammonia are mixed together. Many metal sulfides can be precipitated in liquid ammonia by ammonium sulfide from the nitrate solution of the metals. Ammonolysis. Solver-lysis reaction in liquid ammonia are called ammonolysis or ammonolytic reactions. These are analogous to hydrolysis reaction and involves the attachment of ammonium ion and amide ion to the reactant. For example, hydrolysis of SiCl4 occurs as SiCl4 plus water gives silicic acid. It may be noted that in ammonolysis, an atom or an ion from a substance is replaced by nitrogen containing ion or radical. Some ammonolysis reactions are sulfuryl chlorides reacts with NH3 gives sulfamides plus NH4Cl. CCl4 in liquid ammonia gives NH2 twice. Excess of liquid ammonia, the ammonolysis of TiCl4 occurs in steps. TiCl4 give TiCl3 NH2 again give reaction with NH liquid ammonia TiCl2 NH2 twice TiCl2 NH2 thrice or TiNH2 four times. When organic halides which undergo slow ammonolysis are ammonolyzed at boiling point of liquid ammonia, mixtures of primary, secondary and tertiary amines are obtained. Though ammonia molecule is basic and has strong tendency to accept proton and therefore it will act as a base. However, towards very strong base, it acts as a proton donor. For example, the type of ammonolysis reaction NaH plus NH3 gives NaNH2 plus H2. Complex formation reaction. Many complex formation reactions in liquid ammonia are reported which are similar to reaction occurring in aqueous solvents. For example, zinc nitrate reacts with potassium amide to form insoluble zinc amide which dissolve in excess of amide due to formation of complex compound of zinc. Formation of ammoniates. Just as water from hydrates, ammonia also form ammoniates with many inorganic salts. In these compounds, the ammonium molecules are coordinated to cation. Some typical ammoniates are BF3NH3. Liquid ammonia gives BF3NH3. Redox reactions. Liquid ammonia acts as an excellent medium of redox reaction. In liquid ammonia, the oxidizing reaction of strong oxidizing agents is weaker than in water solution. For example, NO3 in liquid ammonia does not act as an oxidizing agent. Similarly, KMNO4 in liquid ammonia acts as a very weak oxidizing agent. On the other hand, reducing agents show increased reactivity. For example, alkali metal acts as a very powerful reducing agent in liquid ammonia. For example, sodium metal in liquid ammonia reduces CuI to Cu, KMnO4 to 2KMnO4. Solution in liquid ammonia. The dielectric constant of liquid ammonia is low, therefore, it is expected to be poor solvent for ionic substances. Amongst the inorganic compounds, all ammonium salt nitrates, thiocyanates, and iodides are soluble in liquid ammonia. Oxide, hydroxide, carbonate, phosphate, sulfate, and most of the sulfide are insoluble. For most fluoride are insoluble in liquid ammonia, and solubility among halides increases as fluorine, chlorine, bromine, iodine. Most of the iodides are soluble. Calcium and zinc chlorides, which are extremely soluble in water, are quite insoluble in ammonia. Organic compounds such as halogen compound, alcohol, ketone, ester, simple ethers, phenol, amine, and nitro compounds are readily soluble in liquid ammonia. Aromatic hydrocarbon are sparingly soluble. Paraffin and benzene are not soluble. Amongst the elements, metals like Mg, Al, Zn, Ca, La, Ce, Mn are only slightly soluble in liquid ammonia. Alkali metal and alkyl earth metal are highly soluble in liquid ammonia. Therefore, these form very interesting solution, and non-metal like sulfur, phosphorus, iodine, selenium are soluble in liquid ammonia. The most striking property of liquid ammonia is its ability to dissolve alkali metals. The resulting solutions are blue and extremely good electrical conductors. The important characteristic of alkali metal solution are they are blue in color, and color is independent of metal dissolved. When the concentration of metal is increased, the color changes to bronze and show metallic appearance. These solutions are conducting and show strong reducing properties. The solutions are paramagnetic, and the paramagnetic character decreases with increasing concentration. If the reagents are pure and dry, the sodium solution in liquid ammonia are stable and can be preserved for several days. When alkali metals are dissolved in liquid ammonia, they ionize to give metal ions and valence electrons. For example, Na in liquid ammonia gives Na positive an electron. Both alkali metal ion and electron become solvated by ammonia molecules, form ammoniated cation and ammoniated electron. The ammoniated electrons are responsible for blue color of the solution. This is done due to the absorption of visible light by ammoniated electron. The electrical conductance is also due to the ammoniated cations and ammoniated electrons. The conductivity of metal in liquid ammonia is comparable to that of aqueous solution of a typical ionic compound. As the concentration of the solution is increased, the ammoniated cations and electrons associate, resulting in the decrease of conductivity. Very dilute solution of alkali metal in liquid ammonia are metastable, and when crystallized they undergo decomposition. As the concentration of metal increases, the blue color changes to bronze, and finally the blue color disappears altogether. This is due to the fact that impurities such as iron oxide catalyze the conversion of metal into amide. On evaporating the alkali metal ammonia solution, alkali metal can be recovered. The strongly reducing character of these solution is due to presence of readily available electrons. The important application of alkali metal solution in organic chemistry is the reduction of many functional group and unsaturated carbon compounds. As already studied, liquid ammonia is thoroughly studied known aqueous solvents. Some of its advantages and disadvantages as solvents are given. Dissolution of alkali metals without a chemical reaction is one of the greatest advantages of using liquid ammonia as solvent. The dissolved alkali metals can be recovered from the solution by evaporation. The alkali metal solution are strong reducing agent, even stronger than hydrogen. The ammonium salt dissolved in liquid ammonia act as amino acids, and they find applications in preparatory chemistry. The tendency for solubilisis is less in liquid ammonia than in water. Disadvantage of liquid ammonia as solvent. The liquid ranges of liquid ammonia is from minus 33.3 degrees Celsius to 77.7 degrees Celsius. Therefore, a low temperature or high pressure is necessary while working with ammonia. Liquid ammonia has offensive odor, therefore it is required special techniques to use it as a solvent as reaction medium. Liquid ammonia is a hygroscopic in nature, hence all the reactions are to be carried out in sealed tube. Liquid sulfur dioxide is a non-protonic solvent or aprotic solvent because it does not contain any hydrogen atom. It is also one of the important non-aqueous solvent that has been widely used in industry. Under normal condition of temperature and pressure, sulfur dioxide is a gas, but it can be readily liquefied and easily maintained in the liquid phase. It has a wide liquid range -10 degrees Celsius to -75.5 degrees Celsius and can be used as a solvent. It can be easily purified by passing the gas through sulfuric acid and through P2O5 to remove traces of water. Its dielectric constant is small and therefore is a good solvent for covalent compound. Structure of sulfur dioxide molecules. Electron diffraction studies have shown that sulfur dioxide in a gaseous phase has an angular structure. The valence bond theory predicts SO2 molecules is a resonance hybrid of following two resonating structures. Solubility of compound in liquid sulfur dioxide. Among the inorganic compounds, iodides, thiocyanates are most soluble. In case of alkali metal halides, the solubilities are in order Mi, Mbr, Mcl, Mf. The uninegative polyatomic anions such as ClO4 negative, NO3 negative, BF4 negative are generally more soluble in liquid SO2. Source of multi-negative anions such as SO4 2 negative, SO3 2 negative, SO2 negative, O2 negative, etc. are practically insoluble. Many of the ammonium, thallium, and mercuric salts are soluble. It is excellent solvent for covalent compound. Many covalent substances like halogen, interhalogen, and phosphate halides, oxyhalides of sulfur, phosphorus, and halides are soluble in it. Metal are insoluble in liquid SO2. Amongst the organic compound, aromatic hydrocarbon and alkene, pi-bonded compounds have very high solubility in liquid SO2 in comparison to saturated hydrocarbons, alkanes. Pyridine, quinoline, ether, hydrogen, halogen derivatives, and acid chlorides also dissolve in liquid ammonia. Many compounds dissolve in liquid SO2 to solvate formation. For example, Ki4SO2, Ci2,4SO2, KSCnSO2. Many neuron molecules also stable solvent with SO2. Autoionization of SO2. Pure SO2 is a poor conductor of electricity, though it is believed to autoionize as SO2 positive and SO32 negative. The thionyl ion is analogous to hydronium ion, and ammonium ion is and sulfate ion correspond to hydroxyl ion and amide ions of aqueous solvents, aqueous and ammonia systems respectively. The reaction in liquid sulfur dioxide. Acid-base reaction. According to solvent system concept of acid-base, the compounds which give thionyl ions in solution of SO2 would behave as acid, whereas compound which gives sulfide ions in liquid act as a base. Amphoteric behavior is shown by zinc and aluminium ion. For example, AlCl3 reacts with SO32 negative ion in liquid SO2 to form insoluble ammonium sulfite. However, if the precipitation is treated with excess of sulfite, the precipitate re-dissolve. Solvolytic reactions. Ammonium acetate is solvolized in liquid SO2. This reaction is analogous to reaction of ammonium acetate in water. Certain covalent halides such as PCl5P, Br5U, Cl5A, Cl5, WCl6 undergo solvolysis in liquid SO2 in sealed tubes. Many binary halides such as SbCl3, SbCl5, SiCl4, SnCl4, VCl3, SCl2, SCl4, MoCl6 do not undergo solvolysis in liquid sulfur dioxide. The formation of solvates. The addition compounds which with the solvent is also known. Typical example of solvate are Ni4SO2, RBI 4SO2, KBr 4SO2, CAI2 4SO2, BAI2 4SO2, SI2 4SO2. Precipitation reaction. A large number of precipitation reactions can be carried out in liquid sulfur dioxide due to selective solubility of compounds. The precipitation of several soluble compounds in liquid sulfur dioxide can be carried out by treating them with soluble compounds in sulfur dioxide. Complex formation. A large number of complex ion formation in liquid sulfur dioxide have been reported. For example, the solubility of iodine in liquid sulfur dioxide is greatly increased by addition of potassium and rubidium iodide. This is due to the formation of complex Ki and RpI3. Similarly, the increase in the solubility of cadmium iodide and mercury iodide in liquid sulfur dioxide is attributed to the formation of complexes. AlCl3 reacts with SO3 2 negative ions to form precipitate of Al2SO3, which resolve in excess of SO3 2 negative ions, forming the complex ion. Organic reactions. A large number of organic reactions have been carried out in liquid sulfur dioxide because organic compounds are soluble in it and relatively inert solvent. For example, sulfonation of aromatic hydrocarbons by sulfur dioxide and chlorosulfuric acid. Liquid SO2 also has been used for solvent for Friedel-Crafts type reaction. In these reactions, AlCl3 is used as catalyst, which is highly soluble in liquid SO2. It also used as a solvent for addition and substitution of bromine reaction. Sulfur dioxide of crystallization. These reactions are also called solvation reaction, like water and ammonia salts are having sulfur dioxide of crystallization have also been observed. Some examples are sodium iodide 4SO2, Ki 4SO2, Li I2SO2. These are formed with highly soluble salt and are analogous to hydrate. Redox reaction. Though gaseous sulfur dioxide behave both as oxidizing and reducing agent, the liquid sulfur dioxide does not show any marked reducing and oxidizing tendency. It simply acts as a medium for certain redox reaction. For example, iodine is liberated from Ki in presence of SbCl5 in liquid sulfur dioxide. Some special feature of liquid SO2 as a solvent. It has low boiling point and this allows its easy evaporation and therefore removal from reaction mixture. It has low melting point and therefore it follows reaction to be carried out at low temperature. Liquid SO2 is an inert solvent. It has unusual solvating power for both covalent and electrovalent compounds. It is a better medium for covalent compounds like hydrocarbons and is used for purification of some petroleum products. It is used as diluent for the superacid medium HSO3F SBF, which help in reducing its viscosity without affecting the acidity. Now the chapter is over. Thank you for listening the video.